So far, we have considered the impact of offset voltage and the bias currents, the input bias currents on amplifying circuits, which we took examples of inverting, non-inverting, and voltage buffers. And we saw how does offset both the input bias current and the offset voltage, how do they impact the op-amp's performance? Okay, we studied that. We also studied offset nulling circuits for all the amplifier configurations. Now, in this lecture, we will study the impact of op-amp non-idealities like offset, base current, the bias currents, and even noise on frequency-dependent circuits. And two of the most commonly used frequency-dependent circuits are integrators and differentiators. Okay, these are two extremes. So generally, we use low-pass filters and high-pass filters. These are like a very, I mean, I will say integrator can be seen like a low-pass filter because its gain decreases with increasing frequency. And differentiator is also kind of a high-pass circuit. Okay, it passes higher frequencies and attenuates lower frequencies. So we'll study the impact that offsets have on these frequency-dependent circuits. So let's start with the integrator circuit. Let's assume we have, first we'll start with an offset voltage. If I assume there is an offset voltage, what will be the offset, what will be the impact at the output due to the offset voltage? What do you think? The offset is like a DC voltage, right? It's a fixed DC voltage. So this is not time varying or anything. It's fixed. It's a fixed DC voltage. If you apply a fixed DC voltage to an integrator circuit like this at the positive terminal, what do you think will happen? Assume this op-amp is ideal. If you assume this op-amp to be ideal, what do you think will happen at this point? Positive, it's a positive terminal. Yeah, it is amplified by how much? See, what happens at DC? I'm asking you this to keep in mind. V offset is like a DC signal. What happens at DC? What happens to the capacitor? It acts like an open circuit. It's not, I can ignore that I can say that there is no feedback at DC. If there is no feedback at DC, assume your input signal is 0. I'm only analyzing the impact of offset. That will just be equal to A times V of A is your op-amp's DC gain. It will just get amplified by a factor of the op-amp's DC gain. Or for an ideal integrator, assuming the op-amp is ideal, it's infinite. So if your offset voltage is in the order of, say, offset voltages in the order of hundreds of microvolts or some early milliwatts, 1 or 2 millivolts, and your DC gain can be, remember our DC gains can be as high as 10 power 5, right? So that will take it to 200 volts, which means your op-amp's output will saturate. So offset voltages can saturate integrators when operated in open loop. If you just put an op-amp in open loop, the DC offset voltage, that itself can saturate the op-amp's output. Okay, that's one problem. So now let's study the impact of the base currents. The bias currents. I mean, I'm not doing any frequency analysis here because, see, remember, offset voltage and bias currents, they're all DC quantities. They don't change with frequency. If you want to understand how it changes with frequency, we'll come to that. I'll talk when I talk about noise, we'll talk about that. So let's start with the input bias current. You will have IB plus flowing into this terminal. No impact because it's anyways flowing into ground. So it's not a problem. Now IB minus, the path for IB minus is this. See guys, now that I'm analyzing the bias current effects, I'm just directly assuming all the current flows through the cap because now this is a very obvious fact for you guys because you know no current flows through this resistor. Any bias current that's flowing inside the op-amp has to flow through the feedback path and it has to come from the op-amp output. So that's a given knowledge for us now. So I'm directly using that analysis. So if your bias current flows through this capacitor, what do you think will happen to the output voltage again? Let's assume IB minus is now a constant current. Remember, this is a constant current flowing through a capacitor. So if a constant current is flowing through a capacitor, it's like the voltage across the capacitor will be a ramp voltage. So remember the direction of, yes, it's a ramp output and the direction of current is in this way. So it's like you can treat it like you are pumping a current into a capacitor into this node. So this node voltage will just ramp up. Okay. So yeah, this node voltage, the no output node voltage will just ramp up. Again, what is the slope with which it will ramp? It will be IB minus upon C times T. That will be the ramp signal slope. The slope will be just IB minus by C. Okay, since IB minus, the bias current is very small, it would take a really long time for it to reach the supply voltage. See, for example, let's assume the supply voltage is 15 volts and your integrating capacitance is, let's take an example of 10 pico or 100 pico. Okay, let's assume it's 100 picofarads of cap. And 100 pico, then the time when will it reaches, this will be 100 pico by, assume your base current to be 200 nanoamperes, 200 nano. So it will be 15 by 2, which is 7.5 pico nano is 7.5 milliseconds. In 7.5 milliseconds, the output of this op-amp would reach a saturation voltage. Okay. I mean, I'm saying it's long for circuit engineers, but for human experience, 7.5 milliseconds is a very small duration. So when you're simulating the circuit, when you're building the circuit in open loop as an integrator, the output would have already saturated because of the bias current. So you see both offsets and the bias currents can saturate the output. Okay, that's one problem we have. Third, the impact of noise. Noise, there are two types of noise. One is called flicker noise. Flicker noise will have most of its power at low frequencies and it will just decay down as you increase the frequency. And thermal noise is a constant, flat noise source. It's always constant. When you pass thermal noise, again, you can model the noise as a voltage source at this point. Now I need to, noise is frequency dependent. So I need to know that frequency dependent transfer function. So the frequency dependent transfer function for this circuit, it's a non-inverting configuration. So 1 plus Z2 by Z1. Okay, you can analyze it in any way. You can use beta and do 1 by beta, or you can do 1 plus Z2 by Z1. 1 plus Z2 by Z1 is 1 plus Z2 is 1 by SC or SRC. Okay, 1 plus 1 by SRC is the transfer function for our noise from the non-inverting terminal to the output terminal. Okay, so this is your transfer function. So if you substitute S equal to j omega, I can plot, if I plot this transfer function, right, it will look like this. At DC, the value of this function is infinity. It will be infinity, it will keep decreasing. I'm plotting it on a log scale. So this will be a linear graph. Okay. And after a certain frequency, after omega equals 1 by RC, this 1 by SRC term will become smaller, right? 1 by SRC, that term is, after omega greater than 1 by RC, this term will become smaller than 1. From then onwards, it will remain flat like this. This 1 will dominate. 1 plus a number that's smaller than 1, we can ignore it. It'll be constant. See, I'm plotting the magnitude response. The actual response will look something like this. 1 plus 1 by j omega RC, which can be written as 1 minus j by omega RC. So it's a complex number. And at omega equal to RC, the magnitude of the complex number will be root 2. Okay. And after that, it will decay down. It will become flat at 1. So at this point, at this point, it will be root 2 when omega becomes equal to 1 by RC. So again, if you notice this graph, at low frequencies, the noise is getting amplified. So what happens is, whenever you build an op-amp, an integrator in open loop, flicker noise is often called as the low frequency. That low frequency noise is dominated by flicker noise, which will have a profile like this. That can also saturate your op-amp. Okay, the low frequency noise, yeah, can actually saturate your op-amp's output. Fine. So these are the 3 different noise sources, 3 different non-idealities. noise, offsets, offset voltage, and by input bias current. All three of them tend to saturate this output voltage in an open loop. If you just put an integrator in open loop, that's the problem you have. So what do we do to fix it? I have to somehow ensure that the DC gain is finite. And that way, how do you do that? Just put a resistance in parallel with the capacitance. See, what happens is that the gain of this circuit is simply given by ratio of this impedance to this impedance. The problem of infinite transfer function happens because this impedance, one of these two impedances is blowing up to infinity. And since only one guy is frequency dependent, which is capacitor, the capacitance is the troublemaker, right? That's the one which is blowing up to infinity. So therefore, to avoid that, you can simply put a resistor in parallel with it. So at DC, the resistance offered by this network is RF. Once you include RF, now, at DC, it becomes like at DC, I can ignore the capacitor. There is a DC feedback present in the circuit. And this circuit we just analyzed in the previous lecture, right? An inverting amplifier, we saw the different kinds of offset voltages and bias currents and their impacts. And we saw how to deal with them. We know how to deal with offset voltages and bias currents using offset nulling. So we can apply offset nulling on this circuit to take care of those offset and bias current problems. Okay, so you can use offset nulling to take care of that problem. And as far as noise is concerned, this is RF is going to limit my DC gain. So you can quickly derive the transfer function for this circuit. The transfer function for this circuit is going to be minus of RF by R, the DC gain, which you can see that the DC gain, if you remove the capacitor, it's just minus RF by R. The exact expression, you can derive it by taking the ratio of this impedance to this impedance. And that will turn out to be minus of RF by R times 1 by 1 plus SCRF. Okay, see that follows directly from this. The Z feedback divided by Z input, which is R. Z feedback is RF by 1 plus SRC. 1 plus SRFC. So into 1 by R with a minus sign. That's it. So I've just written that expression here. I've taken RF by R common out, and you'll be left with a DC gain and a pole. So if you plot its frequency response in frequency domain, this is how it's going to look. For an ideal integrator, its gain blows up to infinity at DC. This guy is 1 by SRC. And for a practical integrator, where I'm putting a feedback resistor to limit its DC gain, the response will look like this in the green color. Okay, this is a low pass filter. At DC, the gain is RF by R. And once the pole frequency is 1 by RFC, after the pole frequency, the gain will start rolling off and both these responses will match each other. See what happens after the pole frequency, whenever you have this term, right? 1 by 1 plus SRC. This term, after the pole frequency, which is 1 by SRC, the RFC factor will become much greater than 1. So I can ignore that. If I ignore that, this term will be reduced to RF by R times 1 by S RFC. So RF and RF will cancel out and I'll be left with minus 1 by SRC. So for frequencies much greater than the pole, which is 1 by RFC, the integrator and the ideal integrator and the integrator with the feedback resistor are indistinguishable. So I can say in this region after the pole, this circuit with negative feedback will behave like an integrator. With the DC negative feedback resistor, will act like an integrator. Okay, so generally integrators are not used in open loop as it is. We will take some examples later. We'll see where integrators are used. They are often placed inside bigger global negative feedback loops, which will ensure that these outputs don't blow up. Okay, so but if you are going to use it in open loop, usually you will need this integrator to act like an integrator for a range of frequencies. And you can choose your value of RF to ensure that the integration behavior is guaranteed in this range of frequencies you want. Okay, So practical integrators will often have a resistor in the feedback path. Yeah. Now we'll analyze the impact of finite gain on integrators. What do you think will happen to an integrator? Um, I'll assume no offsets are present. So we just discussed once you add a feedback resistor, then it behaves like an integrating amplifier at DC, close to DC. And we saw how to deal with, how to deal with offsets. We can build offset nulling circuits to cancel them out. All that is fine. Now, I just want to take an ideal integrator and then assume that the op-amp's gain is not infinity. Remember, when I'm saying this guy, the op-amp's DC gain is 1 by SRC is the op-amp's DC gain, right? I'm assuming that the op-amp is ideal. Only then it will give you this 1 by SRC characteristic. What happens when the op-amp's gain is finite? It's equal to A. Okay, some finite gain. In that case, what will be the impact of the circuit? Okay. Can you guys quickly try? Can you tell me what will be the DC gain for this circuitry? See, ideally for integrated is 1 by SRC. So DC gain was infinity. For this circuitry, what do you think will be DC gain? Assuming op-amp's gain is finite. So when I'm asking you DC gain, I'm asking you to compute from the input terminal to the output. So at DC, can I assume the capacitor is open circuit? If the capacitor is open circuit, by looking at the circuit, can you tell me what will be the DC gain of the circuit? Input signal is applied to this, just the forward path gain itself. The forward path gain, A itself. That's it. So that's the DC gain. So your circuit will have a finite DC gain. And after a point, it will start behaving like an integrator. So that's what intuition tells you. After a point, your capacitor will start offering you feedback. And as long as you ensure your loop gain to be very large, okay, then see, what happens to the loop gain is that the feedback factor for this circuitry is R and C. This is your feedback network, right? This is V minus, this is V naught. I'm just drawing this part here. If you look at the feedback network, beta is a high pass filter. So it is SRC by 1 plus SRC. Okay. So the feedback factor, the DC gain of the feedback is 0. Beta of 0 is 0. Because the DC gain is 0, loop gain is also, because I've assumed a finite forward path gain, loop gain is 0. Therefore, I can ignore its negative feedback action altogether. The forward path gain will just be equal to minus A itself. Here it is minus A. But since I only asked you about the magnitude, I said mod of A is sufficient, mod of minus A, which is A itself. You can do an exact analysis of this circuit, okay, using KCLs and KVLs and arrive at a result. But since you guys have already done Miller's theorem, right? You can use Miller's theorem and say that if I put a capacitor across an amplifier with a gain of A, remember the gain from this node to this node has a 180 degree phase shift. So the total capacitance seen at this point will be C into 1 plus A. Right? The capacitance will look like a multiplied capacitance at this node. So now if you see, right, the voltage at this point, V minus, can be found out by solving this RC circuit. So here you have a capacitor of C into 1 plus A times R. The transfer function is 1 by 1 plus S R C into 1 plus A. Now you know the gain at this point, V minus. The output voltage is simply equal to what? A times V minus. Your output voltage V naught is simply minus of A times V minus. So use that result and you will get the transfer function V naught by Vi of S is simply minus of A by 1 plus SRC into 1 plus A. So it looks like a low pass filter, but with a DC gain of the op-amp's DC gain itself. And where does the pole occur? The pole occurs at 1 by RC into 1 plus A. Okay. So if your op-amp's gain becomes infinity, the capacitance seen at the referred at the input will become infinity. So this pole will move to DC and this gain will become infinity. Okay. So this guy will move to infinity and this pole will move to DC. So the graph will become like this. It will go to infinity for an ideal op-amp. Okay. So for integrator with a finite gain acts like a low pass filter. And the DC gain of this low pass filter is the op-amp's DC gain itself. Okay. So next, we'll look at differentiator. So for a differentiator, what do you think will be the impact of the all the input base current and offsets? We'll quickly see that. If I put an offset voltage, remember offset is DC. Offset is a DC signal. So if your offset is a DC signal, what will be the impact at the output for a differentiator? Offset is like a, exactly right. Your V naught will simply be equal to VOS, V offset itself. Because at DC, the capacitor, you can treat it like an open circuit and you're left with just a negatively fed back voltage follower. So your output, the positive terminal will follow this and your output terminal will also be equal to V offset. If you assume base current, your base current will bias current that will flow through R and that will be IB minus times R. Okay, that will be IB minus times R. So at the output, you will have V offset plus IB minus times R for a differentiator. Okay, we can again add some form of offset cancellation circuitry and then cancel out these offsets too. There is no big deal with that. But for, see, all I'm trying to say is that for an integrator, these DC quantities like offsets and bias currents were causing huge problems, right? They were saturating the output. But all I'm trying to show here is that it's not as big a deal for differentiators. Okay, DC guys are not the DC non-idealities like offset voltages and input bias currents are not that big of an issue. Okay, but there is one other quantity which becomes a very serious issue, that is noise. Noise is a frequency dependent quantity. Let's assume you have a finite noise. What do you think will happen to this circuit? Op-amp's noise at the input, what will happen? You can solve this equation. This is again, you can use superposition. Assume input is 0, 1 plus R2 by R1, right? R2 by R1 is, it's a non-inverting, in a non-inverting configuration. R2 happens to be R by 1 by SC, which is SRC. This is the transfer function that you see for noise. And if you plot this transfer function, the value of this transfer function at DC is 1. Okay, at DC, the value is 1 or 0 decibels. It will be 1 at DC. After S equal to 1 by RC, after omega equal to 1 by RC. So this function can be written as 1 plus j omega RC. And at omega equal to 1 by RC, it will become root 2 and it will go like this. After omega equal to 1 by RC, it will just keep increasing. It will Bode plot, right? It's an asymptotic plot. It will look, ideal Bode plot will look like this. It will just be different near this corner frequency. So at the corner frequency, this point will be root 2, but Bode plot gives you a good idea, right? You can just plot it using straight lines. So if this is 1 or 0 decibels, the gain starts increasing. So what you see here is that the high frequency gain blows up to infinity. It just keeps increasing indefinitely at very high frequencies. Okay, the gain of this circuit at very high frequencies just blows up to infinity. Oh, so that's the problem with noise. So if you feed any noise into this, and noise generally has two flavors, right? Flicker noise or thermal noise. And thermal noise will generally have energy all over the frequency. I mean, it'll have energy for all frequencies. So all these high frequencies noise will get amplified significantly. So the problem for differentiators is noise. And even your input signal can contain some noise. I mean, input is not just clean input, right? Input can also have an additive noise. So this is Vi, and there can be additive noise at the input itself. So this is, see, what I'm modeling at the positive terminal of the op-amp is the op-amp's noise. The circuits present in the op-amp are adding some noise. This one, the noise I'm talking about, is the noise from external. Maybe the input source itself is noisy. Maybe it's coming from another op-amp whose noise gets differentiated. Therefore, it will blow up. So for a differentiator circuits, ideal open loop differentiators are not used often because of this problem, that the noise can actually blow up. It can amplify the noise too. Okay, so that's one problem. So we'll again do the two things, which is take a differentiator and analyze the performance of a differentiator in the presence of finite DC gain, and also then analyze the impact of finite DC gain on the differentiator, and see if we can fix this problem of noise at high frequencies. See, at high frequencies, what was the DC gain of this? What was the gain of the circuit, which was infinity? Ideally, it was supposed to go to infinity, right? So let me analyze. Yeah, if I take an ideal integrator, assuming that A is infinity, the gain of the op-amp is infinity, the transfer function for this circuit is SRC. Remember, this transfer function that I do, this is noise transfer function. This is not the signals transfer function. Signals transfer function is just SRC with a minus sign. This 1 plus SRC is actually noise transfer function. Okay, just keep that in mind. And here, I'm coming back to this circuit. Now I'm trying to analyze this differentiator. So the transfer function for a differentiator from input to output is minus SRC. Okay. Now, if I assume the op-amp has a finite DC gain, can you tell me what will happen to the transfer current? How will the transfer look like? So for an ideal differentiator, it should just keep increasing like this with increasing frequency. But for a practical differentiator with a finite op-amp's DC gain, what do you expect to happen? See, you can quickly see using some intuitions, saturated A, right? The maximum gain has to be A, the loop gain of the op-amp. Why is that? So what is the feedback network here? The feedback network is C into R. Okay. So at this node, the B minus node, if you look at this B minus node, there are two guys who are competing to impact that voltage. Who are the two? One is the output voltage and the other is the input voltage. As far as the output voltage, the circuit looks something like this. A capacitor, a resistor, this is output, this is input, and you're finding out V minus here. Okay. As far as the input is concerned, if you find the transfer function from input, as you have to assume V naught to be 0, it's a high pass filter. As far as the input is concerned, V minus to V naught is a high pass transfer function. So you'll get a transfer function that looks like this. This is V minus, C, and Vi. As far as the output is concerned, I'm showing this directly here. It will look like a low pass filter. And the sum of the two voltages is what is trying to is what V minus sees. You know, the inverting amplifier sees the sum of these two voltages. So at very high frequencies, your output voltage, very little quantity is fed back. The feedback quantity is getting reduced. As capacitor shorts out, this will become 0. And as capacitor shorts out at very high frequencies, V minus will be mainly determined by Vi itself. So V minus becomes equal to Vi. at very high frequencies. At DC, at very low frequencies, V minus will be equal to 0. V minus will be equal to V minus will be fed back. I mean, most of the signal will be fed back. V minus will be equal to V naught. Most of the signal will be fed back. So at very high frequencies, there is no feedback, and V minus will be equal to Vi. Therefore, your V naught is simply equal to minus of A times Vi. Minus of A times V minus, which is nothing but minus of A times Vi. So that's it. All I'm trying to say is the gain will saturate at some point to a value of A. And the point of transition, you can figure that out by equating these two. So I'll leave that approximately. Again, you can calculate it. Let me say, yeah. So what happens? Can you guys derive that using this very simple intuition? Let's look at it this way. We can use Miller effect. I'll tell you using Miller effect too. But you can also use some very simple intuitions. At low frequencies, the gain is minus SRC. At high frequencies, the gain is A. I can equate the two gains and figure out at what point these two gains become equal. At what point these two curves intersect. Approximately, that will be the pole. So the point of intersection will be, or I shouldn't use the word pole, that's the point after which the gain flattens out. That will be A by RC. Okay, that's the point where A by RC. How does this come about? We can use Miller's theorem also, like we did for integrators. If this is a capacitor here, what is the input resistance seen at this point? Use Miller's theorem. Z by 1 plus A. Capacitors get multiplied by 1 plus A. Resistors get divided by 1 plus A. That's what happens when you apply Miller's theorem. So you will have a circuit that looks like this. Capacitor, resistor of value R by 1 plus A. C. So this is V and V naught. And the transfer function, this is a high-pass filter. So high-pass filter transfer function will be SR C upon 1 plus A divided by 1 plus SR C upon 1 plus A. This gets multiplied by minus A, right? So then you have to multiply with the gain of this amplifier. You are at this point, this is V minus. The transfer function, we have reached V minus. Then from V minus to V naught, you can multiply it by minus A. So the overall transfer function will look something like this. Minus A times SRC by 1 plus A divided by 1 plus SRC by 1 plus A. So this is a high-pass filter with a gain of 0 at DC. And the maximum value of this will be 1, right? High-pass filter, the maximum value of high-pass filter is 1. That happens when this term starts becoming much greater than 1. Then the numerator and denominator will cancel out and you'll be left with minus A. So that's what happens here. And you can see from this expression, you have a pole and you have a 0 at DC and you have a pole at a frequency of 1 plus A by RC. Okay. Using our analysis, we couldn't get an exact answer. We got a near approximate answer, right? So that's still a very good estimate. We said A by RC. It's exactly 1 plus A by RC. And it flattens out at A. So this is the impact for an ideal integrator, but still A can be a really large number. So noise will still get amplified by a huge factor. High frequency noise can get amplified by a huge factor. How do we fix this? Well, I'll just discuss this point alone very quickly. See, anything that we did for integrators, you'll have to do the opposite, the dual of that for differentiators. Okay. So the problem occurs at very high frequencies. I want the gain to decrease or be within control. So what can I do? By looking at this circuit, can you guys say can you do something here? Why is this gain blowing up at high frequencies? There are two impedances that are responsible. This impedance and this impedance, right? The ratio of the gain of the circuit from input to output is simply ratio of this impedance to this impedance. At high frequencies, this impedance is becoming close to 0. See, the capacitor is providing lower and lower impedance. all I need to do is ensure that the capacitor impedance is finite after a certain frequency. So just add a resistor in series. So let's call R1 as a resistor in series. If I do that, what will be the very high frequency gain of the circuit? Very high frequency gain of the circuit will simply be minus of R by R1. That's it. So now I've limited the DC gain of the circuit, but I have modified the whole bunch of other things. Okay, so now the moment I introduce a resistor, R1C, so then we'll treat this like an ideal op-amp. See, A is a very large number, so this pole will occur at a very high frequency, so you can ignore this. So we'll treat this op-amp like an ideal op-amp and try to figure out draw the transfer function for this. You can also use mathematics and directly draw it, but let's use basic and intuitions, right? At DC, it's a capacitor, so the transfer function will be SRC. So it on a log scale, it will be minus infinity, right? Omega equal to 0 will be minus infinity. So I'm plotting it on a log scale. And then at some point, you want this to flatten out. It's just increasing. At some point, the resistive impedance here will start dominating the capacitive impedance. That happens when R1 becomes equal to 1 by SC. So S is equal to 1 by R1C. At that pole frequency, which is R1C, 1 by R1C, the transfer function starts to flatten out after the pole. And that value will be, the gain value will be R by R1. Now, let me further pose another question. I'll tell you that I want the gain of this high frequency gain to not even be flat. I don't want, because this maybe R by R1 can be a large number. Obviously, R will be greater than R1. So in that case, I don't want this gain. I want this gain to further roll down. What can I do? If I want this gain to roll down, what can I do? Again, use the same logic. The gain at these high frequencies is determined by the impedance at this feedback path and the input path. I want to decrease the impedance of the feedback path. Then what do I do? Just add a capacitor in parallel. Let's call it some C feedback capacitor in parallel. And after some frequency, which is 1 by R into CF, it will start flattening out. We'll talk more about this when we talk about practical differentiators. Okay. I just want to introduce you right now how to think about designing the transfer characteristics to your advantage. Okay. So I'll stop at this point. We'll continue next.